Hi, I have just returned from a wonderful lunch at somewhere called Søllerød Kro, north of Copenhagen. Lovely lunch, not too large, and it tasted wonderful. And I'm relaxed and happy, so let's see if I'm able to do some math in this state. Exactly 3 FQ points of order 3. And we just take the curve from the problem 4. And A is a rational number, and it maps into FQ somehow. So let's just take it as a point of FQ. So let's just say that A lies in FQ. And of course, point of order 3, I immediately thought about this formula that we have had a lot of times. It's 2/3 square root 3. But that works for the curve. And I've been thinking it must be possible to have a simple way of finding the points of inflection on an algebraic curve. And I looked a little around on the net. There was nothing on Wikipedia, but I found a master, a piece of paper, master thesis, I think it's called, a master thesis, where the problem was handled. And it's very, very simple. When we have an algebraic curve, and let's take the one we already know, y squared minus x to the third plus n squared x, and the projective completion. So we write up the Hessian. This may, of course, be very well known to you, but it was the first time I saw the result, and I really liked projective geometry because there are so good formulas, but this one I didn't know. So we differentiate twice with respect to x. Only x to the third survives. Once with respect to x, then with respect to y. Once with respect to x, n squared, z squared, then with respect to z. Twice with respect to y. First with respect to y, 2yz, then with respect to z, and finally twice with respect to z. So this determinant it actually has quite a lot of terms. It should give the equation we already have. So let's do it one step at a time. 24 x n squared x squared z. And we should be able to checking the order. This is order 3, so they all have order 1. So the determinant should have order 3. Yes. Naught minus 8 n to the fourth set to the third. That was this guy up, then this gives naught, and finally minus 24 xy squared. And of course we know that the point at infinity is point of inflection, so it's just set equal to unity. So we only get the affine points. We see y occurs here squared, so we have to use the equation to simplify it, and we can divide by 8, of course. So it's 3n squared x squared minus 2n to the fourth minus 3x to the fourth plus 3n squared x squared. And you know I can't do these things very well, so you never change sign. 3x to the fourth minus 6n squared x squared plus 2n to the fourth. So that should be the equation for inflection points. You check that I've got the right equation. I probably haven't, but that's the method. Now we shall use that on the algebraic curve of this problem. X. That gives like minus 6, so this is already the first mistake. Oops. And now what's wrong here? No, that's true. It's set to the third. Divide by x and then y, twice with respect to y, one with respect to y, once with respect to z, and twice with respect to z. That's 6az. So that's minus 6x times 12az squared minus 4y squared. You take 4 outside, minus 24x times 3az squared minus y squared. And then we have to use the equation for y. That's a times 3az squared, and y squared is x to the third that's not good. That's not what it is. So we have to take exception for z here to make the reduction. So assuming we have to distinguish two cases. The first, that's if z vanishes, So the point, we'll get the point of infinity, of course. Then it's minus, that's plus 24xy. And if we may set z equal to unity, then it's 24x times, we have 3a, and minus y squared, that's minus x to the third plus a. So it gives 24x times 4a minus x to the third. Whoops! Now, when z vanishes, if x vanishes, then y may be anything. Oh yeah, so that's the point. At infinity we get the effect. If y vanishes and z vanishes, then x must vanish as well. So that point doesn't exist. So this condition just gives us the point at infinity. And now down here, if x is nothing, then y is as well. No, then y is the square root of minus a. I think we need a new paper for this. X to the third, no, 4a minus x to the third. And of course, y squared equals x to the third minus a. So, 1, x might vanish. In that case, y equals square root of minus a. So that's one point. And the next, that's if z to the third equals 4a, then y squared equals 3a. So y has to be square root 3a plus minus. We do get 1 point, the unity. So I need to show that we get the 2 points here. Either this or this guy. So we have to show that either minus a or 3a is a square. If q is congruent to 2 modulo 3. We know there are q plus 1 elements, so we know that 3 divides the order of the group. So there should be at least 2 elements of order 3. So either we have to show there are exactly 2 points, so it's not both. And there was something about the number -3 as far as I remember. What do we have about -3? -3 is not a square. And now we can write -a. Nah, let's do it the other. 3a over p equals -3 over p times, now what's that? Times -a over p. That was a lapse of concentration, so the lunch is taking a toll. So these two guys have opposite sign, so that means that one of them and only one of them is a square, proving that either these points or these points lie on the curve. So therefore we have exactly 2 non-trivial points of order 3. I think I'm done.